In this section, we'll expand a little bit about what we were talking about last time. Last time we were talking about whether you could write something as a linear combination of another vector. Well, now we'll take a look at that and then also linear dependence and independence. So if you remember writing things as a linear combination, let's say you had some vector v. Could you write that vector as a linear combination of other vectors? So let's say c1u1 plus c2u2 plus c3u3, where those c sub n's are constants, and then those u's are vectors. So we're going to do that until we get to the nth vector. So c sub n, u sub n. Okay? That's what we would call a linear combination. Can you write vectors as linear combinations? Well, you could try some very basic techniques. Suppose you had two vectors. So let's say vector u is the vector 0, negative 2, 2. And vector v is the vector 1, 3, negative 1. My question is w a linear combination of u and v? That a is not really a subscript, although I realize it looks like it the way I wrote it. So I'm going to give you a couple of w's, and we'll see whether w is a linear combination of u and v. So my first w is this. W equals 2, 2, 2. All right, what does that mean to be a linear combination? That means that I can write 2, 2, 2 as c1 times 0, negative 2, 2 plus c2 times 1, 3, negative 1. Now, this one you might be able to do by sort of inspection. What's the first line? The first line is 2 equals c sub 1 times 0 plus c sub 2 times 1. Well, that's 0, and you end up with what? 2 is equal to c sub 2. All right, now do the second ones. 2 equals negative 2c sub 1 plus 3c sub 2. Well, if c sub 1 is really 2, c sub 2 is really 2, you'll get 2 equals negative 2c sub 1 plus 3 times 2. Subtract a 6 from both sides, and you get negative 4 equals negative 2c sub 1, which means that 2 is equal to c sub 1. But you're not done yet, because you want to check and see if 2 and 2 are actually the answers. Let's try it. Let's try the third set of equations, which is 2 equals 2c sub 1 plus negative 1c sub 2, and we'll try c sub 1. It turns out in this case they're both equal to 2. So does 2 equal 2 times 2 plus negative 2? Sure. 4 minus 2 is 2. Yes. So is w a linear combination of u and v? In this case, yes, because even though there's only two vectors, when I set it up, I come up with coefficients that work in both cases. All right, let's try another set. Let's try the same vectors, except this time I'll use vector w equals 0, 4, 5. All right, so same equation. Can I write 0, 4, 5 as a linear combination of 0, negative 2, 2, and the second vector 1, 3, negative 1? All right, so let's look at the first ones. The first one would be 0 equals c sub 1 times 0 plus 1c sub 2. So that leads me to believe that c sub 2 is 0. All right, let's try the second equation. 4 equals negative 2c sub 1 plus 3c sub 2. Well, we said we figured out that c sub 2 was 0, so divide both sides by negative 2, and it looks like c sub 1 is negative 2. Let's see if those work in the third set of equations. The third set of equations are 5 equals 2c sub 1 minus c sub 2. So does 5 equal 2 times negative 2 minus 0? No, because it gives me 5 on this side, negative 4 on that side. So that's one way you'll know that it doesn't work. If you're solving a system and you come up with variables that work in some places but not others, then you haven't found a solution to the system. And if a solution to that system doesn't exist, then you cannot write the one vector as a linear combination of others. All right, how about matrices? Do you think you can write matrices as linear combinations of each other? Well, yes, sometimes you can, and sometimes you can't. Depends on the matrices. So let's take matrix A to be matrix 2, -3, 4, 1. And matrix B to be 0, 5, 1, -2. And matrix C to be 6, 2, 9, and 11. All right. Question is matrix C a linear combination of A and B? Well, if it is, then 6, 2, 9, 11 equals C sub 1 times 2, -3, 4, 1 plus C sub 2 times 0, 5, 1, -2. All right, this looks like I'm going to have 4 equations that come out of this. So let's start with row 1, column 1. I get 2C sub 1 plus 0C sub 2 is equal to 6. Let's do row 1, column 2. I get -3C sub 1 plus 5C sub 2 equals 2. Let's jump down to row 2. I get 4C sub 1 plus C sub 2 equals 9. And I get C sub 1 minus 2C sub 2 equals 11. Let's organize this into a matrix to try to solve this. This gives me 2, 0, 6, -3, 5, 2, 4, 1, 9, 1, -2, 11. All right, let's row reduce this. If I try to get rid of some of the zeros in that first column, I can do row 1 minus 2 row 4. Answer goes in row 4. So let's try that. Well, actually, first thing is I'll take the top row and divide it by 2. 1, 0, 3 is now my first row across. If I do row 1 minus 2 row 4, that'll give me -2, +4, -22. So 2 plus a -2 is 0. 0 plus 4 is 4. 6 minus 22 is -16. All right, now let's get rid of the second row. So if I do, third row. So if I do 2 row 1 minus row 3, answer goes in row 3. So double row 1, that gives me 4, 0, 12. And so now 4 minus 4 is 0. 0 minus 1 is -1. 12 minus 9 is 3. All right, so the next one's going to be a little bit more complicated, right? So I'm going to have to do 3 row 1 plus 2 row 2. Answer goes in row 2. So 3 row 1, 2 times 3 is 6. 6 times 3 is 18. Next one multiplied by 2, so I get -6, +10, +4. Add those together, that's my row 2. So I get 0, 10, 22. All right, let's simplify this a little bit. I get 1, 0, 3, 0, 1, 22 tenths is 11 fifths, 0, 1, -3, 0, 1, -4. All right. So we seem to be in agreement that C sub 1 is 3. When I look at this, though, I get C sub 2 is 11 fifths, -3, -4. Yeah, not possible. Because there's no way I can get 3 different answers out of that. Therefore, I cannot write that matrix as a linear combination of the other 2 matrices. If I solved this and got something that worked, then yes, then I could write the matrix as a linear combination of the other matrix. And it might be like a 1, 0, 3, and then 0, 1, 5, and then 0, 1, 5, and then 0, 1, 5 again, right? That's a possibility too. All right, let's take a look then at another concept that's going to come out of this, and that is the concept of a spanning set. A spanning set. Basically, if you've got some set, and every vector in that vector space can be written as a linear combination of the vectors in some set, then that set is a spanning set. So the spanning set, in very short term, contains all of the linear combinations of a set of vectors. In more formal definition terms, it looks like this. And I'm going to write a sort of a sketch, and then you can see the whole formal definition written out in the textbook. So suppose I've got vector v sub 1, v sub 2, all the way out to v sub n. So this is a set of vectors. This is a set of vectors that is the subset of vector space V. So I'm not calling it a subspace, I'm calling it a subset. So it's a subset of some larger vector set, a vector space. So then S is a spanning set of V when every vector in V can be written as a linear combination of the vectors in S. And so what we would say there is that set S spans V. So in other words, suppose I gave you R3, and I gave you a set of vectors in R3. Is it possible to write every single vector in R3 as a linear combination of those given vectors? Sometimes it is. Suppose I gave you the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. I'll bet you it's possible to write every vector as a linear combination of those three vectors. All right, so if that's I, that's j, that's k, you know you can write any vector as a linear combination of I, j, k. So we would say that this set of vectors, right, in this case, this set of vectors spans R3. Everything in R3 can be written as a linear combination of those set of vectors. The span, then, is the linear combination of all those vectors. So the span of set S is that set that goes C1, V1, comma, C2, V2, comma, C3, V3, Cn, Vn. All right, so I've got all these vectors. The span is a linear combination. The span is that set of all linear combinations. The span itself is a subspace of the bigger vector set. So the span is actually a subspace of the vector space V. And it's the smallest subspace that contains every possible linear combination. So if you have ones that are redundant or you have ones that are scalar multiples of each other, then you wouldn't include those extras. You would only include the ones that are absolutely necessary. So it's the smallest possible set. So look at vectors in R2. Suppose I've got vectors like this. So this is k1 times vector 1. This thing over here is k2 times vector 2. What does the span look like? The span is the plane that's defined by those linear combinations. So if I have a plane that goes out like this, or a vector that lies on a plane, I've got k1 v1 plus k2 v2. So the span of those two vectors, v1, v2, is the plane defined in R2 by v1, v2. All right, so it's a whole plane. So the span, in a physical sense, is, in this case, a plane. So how do these things work? How do we test to see whether or not a vector or a set of vectors spans a bigger set. So let's start with R3. Here's the question. Do the vectors 1, 1, 2, 1, 0, 1, and 2, 1, 3 span R3? Well, what I'd like to know is if I can write any vector in R3 as a linear combination of those three vectors. So can I write any vector in R3? Let's call it U1, U2, U3. Can I write that as a linear combination of those vectors? Let's try it. Let's try setting U1, U2, U3, so three elements in vector U, as C sub 1 times 1, 1, 2, plus C sub 2 times 1, 0, 1, plus C sub 3 times 2, 1, 3. You realize what's going to happen is when I set up my three equations, all the coefficients of the C sub 1s are going to go down the first row. All the coefficients of C sub 2 are going to go down the second row. So I got 1, 1, 2. Then this thing should be 1, 0, 1, and this thing should be 2, 1, 3. All right, if I multiply that by C1, C2, C3, then I should come up with U1, U2, U3. Well, what was the old trick? We had looked in the last chapter calling this A, X equals B, and we said if I can make this X equals A inverse times B, I can get a solution to this system. What has to be true in order to make that solution? That matrix A has to have an inverse. The first question then will be look at the determinant of matrix A. If the determinant is 0, then there's no inverse, and I can't solve the system. If the determinant is not 0, then I can find the inverse and come up with a solution to my system. So let's try to find the determinant. I'm going to do 1 times the 2 by 2 determinant 0, 1, 1, 3, minus 1, 1, 1, 2, 3, and then 2, 1, 0, 2, 1. All right, that gives me 1 times 0 minus 1, minus 1 times 3 minus 2, which is 1, plus 2 times 1 minus 0. So negative 1 minus 1 plus 2 equals 0. So if the determinant is equal to 0, then that implies that there's no inverse. And if there's no inverse, then there's no solution. And if there's no solution, then it doesn't span R3. It's not possible to write every three-space vector as a linear combination of those three vectors that I gave you. Surprisingly enough, there are cases where it does work, right? There are cases where you can write vectors as linear combinations of other vectors, and any three-space vector that you want can be written as a linear combination of three seemingly random vectors. Doesn't always work, as we just found out. All right, let's look at another set. All right, let's look at the set 1x, x squared, x to the third. Does S span P3? Remember, P3 means a set of all polynomials of degree 3 or less. So what does that look like? If I write the linear combination out, I'm going to end up with what? C sub 1 times 1 plus C sub 2 times x plus C sub 3 times x squared plus C sub 4 times x to the third. Yeah, it works. Any polynomial of degree 3 or less can be written as a linear combination of scalars and the elements in that set. So any polynomial of degree 3 or less can be written as a linear combination of those 4 elements in the set that I just gave you. Okay, I'm going to stop here and we're going to do a second video on linear independence.